Hello everyone. There is another session of the studying computer graphics using BG. Oh my god, what's going on with my throat? BGFX. Today was kind of day where I could not just sit for the second, so I sit up for a second and was thinking, okay, I'm going to start streaming and study computer graphics. And somebody called me, texted me, need to do something, and it was like a whole day like this. It's like as soon as I sit up and okay, let's set up the streaming, do stuff, and something happened. Anyways, also I guess there is another thing. I just woke up like at 12 or 11 because I wasn't able to get to sleep until 4 a.m. And this happened because my friend yesterday convinced me to have a tea in the evening, and tea has caffeine and it's affect me, and I just could not sleep. I should be more resistant to that stuff. Okay, so did I compile this? I think I did. So yesterday I did not stream, but I did do some work, and essentially were able to load the model using a simple library. So I can demo you. So here we go. There is a model, but the materials are not taken care of yet. So I need to take care about materials. But you can see there is a specular should do the stuff. I don't know if you can see it or not. Yeah, like you saw like a sheen here or here. So this part is more shiny than wooden part. And yeah, you can do models. So I made like this coursed model in Blender. So it looks like this. I don't know. Shininess doesn't work. So maybe let me see. Oh, it's set to roughness. I think it's wrong. It should be set to metallic probably. Or it should be set to roughness. Wait a second. This is normal, right? Yeah, it's an... Oh, it says specular. Oh, yeah, it should be specular. I guess I should... yeah, I should invert it. So, size... How I... length. Let's get the length of this, right? And because it's a color, I guess it should be subtract. And I guess we do like this. And connect to roughness. Did it work? Let me see. So let me connect to base. Oh, so this should be way more darker, and it's not. I'm wondering why. I guess this is something like this. Right? Anyways, I'm not sure this is the right way, but I guess this one should go to metallic, maybe. I don't know. I'm just a bit confused on how it's gonna work with the loader, right? Because it's obviously not going to put this in the gel in the export format. So let's see. So put it here. Selected object, and I think that's it. Export. So let's run it. It's still doing thing. So let's see what kind of materials it's going to print. So this is materials, load material texture, load texture source, long loading texture, star.c star, something like this. Let's see. So there is no textures. No, it says loading texture, but it's pointer 0. Star 0. Mm. I'm wondering if I do it this way. Let's see. Did I save? No, it's. Oh my god, what's this? Am I getting sick? Loading texture. Mm. Image texture. So if I do it like this. Oh, it's taking from alpha. um, so I think I. Oh my god. That's it. I'm going to probably be sick tomorrow. So let's see, how did I do it in Napier? Cookie. shading. There is only base color map. And I'm pretty sure I was saving it. Let's see what format. Oh well, I was doing FBX format, so if I do FBX, let's try FBX. Test model. So let's see if FBX would do. FBX. Test model selected object. X forward. Z up. Export. So now test. Let's do FBX here. So it loaded it. Oh, look at this. Wooden container.png. Okay. So if we connect to roughness, export FBX, export. Nope. Maybe if I connect it like this. What is this roughness? Roughness. Why there is a tool? No. Connect like this. Nope. Specular. Maybe this is what we need. Tint. So I'll go away. FBX. Nope. Hey, we've got it. Okay. So we've got this one and we got this one. Cool. So we remove this. Oh my, what just happened? Test model FBX. I guess I should remove this one. GLB. GLB. Deleted. Okay, nothing makes sense. So load material texture, type name, type get texture. Load texture, ID is texture handle, and material diffuse, material specular. So we've got vector of textures. Be right back. So we have list of textures, diffuse map, and it goes to textures. Texture handle, and this handle is leaking. This handle is leaking. Make this handle not to leak.
Make this handle not leak.
So we have textures, and in the draw we want to iterate through textures. And as us apply them. So let's look how we do it. Set texture, right? And so we have text ID, and we do bgfx set texture text ID plus plus, and texture dot type equal so type and texture diffuse, it would do material diffuse. Otherwise it would do material specular. I guess this is not very accurate. So I guess mesh let me just pass uniforms. So I'll just make it simple. material diffuse, material specular. Let's do it like this. Why you're not happy? 3 arguments, 2 past, set texture. And texture.id. Yeah, and it's just working. Yeah, I guess we are going to say the where is it? Oh, it's here somehow. Model loading is done, kind of done. There is like cutting some corners, but I think I understanding the idea of loading models, so then I would be able to make it work. So let's say this part is done. So I would be interested to I don't know, because yeah, so like right now loading model supports only 2 textures. It does not support multiple textures, and shader does not also supporting multiple textures, but yeah, anyways, I think we're good, and we now can go to the advanced OpenGL part. Dev testing we already covered. Previously, so I do not know why we have it here. Anyways, let's make the commit. Yeah, so there is a handle leaking. I mean, it's like whatever, I don't care. Make model loading kind of work. I mean,
Make the model load and kind of work.
I do understand the theory and everything else. Then I kind of go to the real deal. I would be able to do it properly, and right now I'm just learning how to do this stuff, right? So we can cut corners.
In the coordinate systems chapter, we've rendered a 3D container and made use of a depth buffer to prevent triangles rendering in the front while they're supposed to be behind other triangles. In this chapter, we're going to elaborate a bit more on those depth values the depth buffer or Z buffer stores, and how it actually determines if a fragment is in front. The depth buffer is a buffer that, just like the color buffer that stores all the fragment colors, the visual output stores information per fragment and has the same width and height as the color buffer. The depth buffer is automatically created by the windowing system and stores its depth values as 16, 24, or 32-bit floats. In most systems, you'll see a depth buffer with a precision of 24 bits. When depth testing is enabled, OpenGL tests the depth value of a fragment against the content of the depth buffer. OpenGL performs a depth test, and if this test passes, the fragment is rendered, and the depth buffer is updated with the new depth value. If the depth test fails, the fragment is discarded. Depth testing is done in screenspace after the fragment shader has run and after the stencil test, which we'll get to in the next chapter. The screenspace coordinates relate directly to the viewport defined by OpenGL's GL viewport function and can be accessed via GLSL built-in GL frag coord variable in the fragment shader. The X and Y components of GL frag coord represent the fragment's screenspace coordinates, with 0, 0 being the bottom left corner. The GL frag coord variable also contains a Z component, which contains the depth value of the fragment. This Z value is the value that is compared to the depth buffer's content. Today, most GPUs support a hardware feature called early depth testing. Early depth testing allows the depth test to run before the fragment shader runs. Whenever it is clear a fragment isn't going to be visible, it is behind other objects, we can prematurely discard the fragment. Fragment shaders are usually quite expensive, so wherever we can avoid running them, we should. A restriction on the fragment shader for early depth testing is that you shouldn't write to the fragment's depth value. If a fragment shader would write to its depth value, early depth testing is impossible. OpenGL won't be able to figure out the depth value beforehand. Depth testing is disabled by default, so to enable depth testing, we need to enable it with the GL depth test option. Once enabled, OpenGL automatically stores fragments their Z-values in the depth buffer if they pass the depth test and discards fragments if they failed the depth test accordingly. If you have depth testing enabled, you should also clear the depth buffer before each frame using GL depth buffer byte. Otherwise, you're stuck with the depth values from last frame. There are certain scenarios imaginable where you want to perform the depth test on all fragments and discard them accordingly, but not update the depth buffer. Basically, you're temporarily using a read-only depth buffer. OpenGL allows us to disable writing to the depth buffer by setting its depth mask to GL false. OpenGL allows us to modify the comparison operators it uses for the depth test. This allows us to control when OpenGL should pass or discard fragments and when to update the depth buffer. We can set the comparison operator or depth function by calling GL-depth-func. The function accepts several comparison operators that are listed in the table below. GL always, the depth test always passes. GL never, the depth test never passes. GL less passes if the fragment's depth value is less than the stored depth value. GL equal passes if the fragment's depth value is equal to the stored depth value. GL equal passes if the fragment's depth value is less than or equal to the stored depth value. GL greater passes if the fragment's depth value is greater than the stored depth value. GL notequal passes if the fragment's depth value is not equal to the stored depth value. GL gequal passes if the fragment's depth value is greater than or equal to the stored depth value. By default, the depth function GLS is used that discards all the fragments that have a depth value higher than or equal to the current depth buffer's value. Let's show the effect that changing the depth function has on the visual output. We'll use a fresh code setup that displays a basic scene with two textured cubes sitting on a textured floor with no lighting. You can find the source code at /src/4.advancedopengl/1.1 depth testing/. Within the source code, we changed the depth function to GL always. This simulates the same behavior we get if we didn't enable depth testing. The depth test always passes, so the fragments that are drawn last are rendered in front of the fragments that were drawn before, even though they should have been at the front. Since we've drawn the floor plane last, the plane's fragments overwrite each of the container's previously written fragments. Depth value precision. The depth buffer contains depth values between 0.0 and 1.0, and it compares its content with the z-values of all the objects in the scene, as seen from the viewer. These z-values in view space can be any value between the projection frustum's near and far plane. We thus need some way to transform these view space z-values to the range of 0, 1, and one way is to linearly transform them. The following linear equation transforms the z-value to a depth value between 0.0 and 1.0. F depth equals z minus near fr minus near here near and fr are the near and far values we used to provide to the projection matrix to set the visible frustum C coordinate system chapter. The equation takes a depth value z within the frustum and transforms it to the range 0, 1. The relation between the z value and its corresponding depth value is presented in the following graph. Note that all equations give a depth value close to 0.0 when the object
selection here is so annoying.
The object is close by, and a depth value close to 1.0 when the object is close to the far plane. In practice, however, a linear depth buffer like this is almost never used. Because of projection properties, a nonlinear depth equation is used that is proportional to 1/z. The result is that we get enormous precision when z is small and much less precision when z is far away. Since the nonlinear function is proportional to 1/z, z values between 1.0 and 2.0 would result in depth values between 1.0 and 0.5, which is half of the 0,1 range, giving us enormous precision at small z values. Z values between 50.0 and 100.0 would account for only 2% of the 0,1 range. Such an equation, that also takes near and far distances into account, is given below. F depth equals 1/z minus 1/near 1/fr minus 1/near. Don't worry if you don't know exactly what is going on with this equation. The important thing to remember is that the values in the depth buffer are not linear in clip space, they are linear in view space before the projection matrix is applied. A value of 0.5 in the depth buffer does not mean the pixel's z value is halfway in the frustum. The z value of the vertex is actually quite close to the near plane. You can see the nonlinear relation between the z value and the resulting depth buffer's value in the following graph. As you can see, the depth values are greatly determined by the small z values, giving us large depth precision to the objects close by. The equation to transform z values from the viewer's perspective is embedded within the projection matrix, so when we transform vertex coordinates from view to clip, and then to screen space, the nonlinear equation is applied. The effect of this nonlinear equation quickly becomes apparent when we try to visualize the depth buffer. Visualizing the depth buffer, we know that the z value of the built-in GL frag chord vector in the fragment shader contains the depth value of that particular fragment. If we were to output this depth value of the fragment as a color, we could display the depth values of all the fragments in the scene. If you then run the program, you'll probably notice that everything is white, making it look like all of our depth values are the maximum depth value of 1.0. So why aren't any of the depth values closer to 0.0 and thus darker? In the previous section, we described that depth values in screen space are nonlinear, e.g. they have a very high precision for small z values and a low precision for large z values. The depth value of the fragment increases rapidly over distance, so almost all the vertices have values close to 1.0. If we were to carefully move really close to an object, you may eventually see the colors getting darker, their z values becoming smaller.
So let's try this thing. Copy. So I can close probably that one. I can do probably in here, right? So I'll just put this guy here. GL frag color. GL frag chord. So let's see. It's white. Oh, so if we coming closer to that thing, it's becoming okay. So
if you then run the program, you'll probably notice that everything is white, making it look like all of our depth values are the maximum depth value of 1.0. So why aren't any of the depth values closer to 0.0 and thus darker? In the previous section, we described that depth values in screen space are nonlinear. For example, they have a very high precision for small z values and a low precision for large z values. The depth value of the fragment increases rapidly over distance, so almost all the vertices have values close to 1.0. If we were to carefully move really close to an object, you may eventually see the colors getting darker, their z values becoming smaller. This clearly shows the nonlinearity of the depth value. Objects close by have a much larger effect on the depth value than objects far away. Only moving a few inches can result in the colors going from dark to completely white. We can, however, transform the nonlinear depth values of the fragment back to its linear sibling. To achieve this, we basically need to reverse the process of projection for the depth values alone. This means we have to first retransform the depth values from the range 0,1 to normalized device coordinates in the range 1,1. Then we want to reverse the nonlinear equation 2 as done in the projection matrix and apply this inversed equation to the resulting depth value. The result is then a linear depth value.
Anyways, give me a formula. So this is the formula. So this is the function. So let me put the function here. Right, and linearize. Okay, so this is the cool one. Copy and just put it here. Should be good to go. It did not compile, of course. Frag color, okay. It should be GL. Okay. So if you go far away, it becomes white. If you go closer, it's become darker and darker. Cool. This would be interesting to see. So this is like about 2 meters, right? So like let's do like a 5 meters range. That would be more interesting to see, right? Yeah, so it's like more interesting, like far away and closer. Yeah, cool.
Because the linearized depth values range from near to far, most of its values will be above 1.0 and displayed as completely white. By dividing the linear depth value by far in the main function, we convert the linear depth value to the range 0, 1. This way we can gradually see the scene become brighter the closer the fragments are to the projection frustum's far plane, which works better for visualization purposes. If we now run the application, we get depth values that are linear over distance. Try moving around the scene to see the depth values change in a linear fashion. The colors are mostly black because the depth values range linearly from the near plane 0.1 to the far plane 100, which is still quite far away from us. The result is that we're relatively close to the near plane and therefore get lower, darker depth values. Z-fighting, a common visual artifact, may occur when two planes or triangles are so closely aligned to each other that the depth buffer does not have enough precision to figure out which one of the two shapes is in front of the other. The result is that the two shapes continually seem to switch order, which causes weird, glitchy patterns. This is called Z-fighting because it looks like the shapes are fighting over who gets on top. In the scene we've been using so far, there are a few spots where Z-fighting can be noticed. The containers were placed at the exact height of the floor, which means the bottom plane of the container is coplanar with the floor plane. The depth values of both planes are then the same, so the resulting depth test has no way of figuring out which is the right one. If you move the camera inside one of the containers, the effects are clearly visible. The bottom part of the container is constantly switching between the container's plane and the floor's plane in A. Z-fighting is a common problem with depth buffers, and it's generally more noticeable when objects are further away because the depth buffer has less precision at larger Z values. Z-fighting can't be completely prevented, but there are a few tricks that will help to mitigate or completely prevent Z-fighting in your scene. Z-fighting, the first and most important trick is never place objects too close to each other in a way that some of their triangles closely overlap. By creating a small offset between two objects, you can completely remove Z-fighting between the two objects. In the case of the containers and the plane, we could have easily moved the containers slightly upwards in the positive Y direction. The small change of the containers' positions would probably not be noticeable at all and would completely reduce the Z-fighting. However, this requires manual intervention of each of the objects and thorough testing to make sure no objects in a scene produce Z-fighting. A second trick is to set the near plane as far as possible. In one of the previous sections, we've discussed that precision is extremely large when close to the near plane, so if we move the near plane away from the viewer, we'll have significantly greater precision over the entire frustum range. However, setting the near plane too far could cause clipping of near objects, so it is usually a matter of tweaking and experimentation to figure out the best near distance for your scene. Another great trick at the cost of some performance is to use a higher precision depth buffer. Most depth buffers have a precision of 24 bits, but most GPUs nowadays support 32-bit depth buffers, increasing the precision by a significant amount. So at the cost of some performance, you'll get much more precision with depth testing, reducing Z-fighting. The three techniques we've discussed are the most common and easy to implement anti-Z-fighting techniques. There are some other techniques out there that require a lot more work and still won't completely disable Z-fighting. Z-fighting is a common issue, but if you use the proper combination of the listed techniques, you probably won't need to deal with Z-fighting that much.
Stencil testing.
Stencil testing. Once the fragment shader has processed the fragment, a so-called stencil test is executed that, just like the depth test, has the option to discard fragments. After that, the remaining fragments are passed to the depth test, where OpenGL could possibly discard even more fragments. The stencil test is based on the content of yet another buffer called the stencil buffer that we're allowed to update during rendering to achieve interesting effects. A stencil buffer usually contains 8 bits per stencil value that amounts to a total of 256 different stencil values per pixel. We can set these stencil values to values of our liking, and we can discard or keep fragments whenever a particular fragment has a certain stencil value. Each windowing library needs to set up a stencil buffer for you. GLFW does this automatically, so we don't have to tell GLFW to create one. But other windowing libraries may not create a stencil buffer by default, so be sure to check your library's documentation. A simple example of a stencil buffer is shown below, pixels not to scale. The stencil buffer is first cleared with zeros, and then an open rectangle of 1 is stored in the stencil buffer. The fragments of the scene are then only rendered, the others are discarded wherever the stencil value of that fragment contains a 1. Stencil buffer operations allow us to set the stencil buffer at specific values wherever we're rendering fragments. By changing the content of the stencil buffer while we're rendering, we're writing to the stencil buffer. In the same or following frame S, we can read these values to discard or pass certain fragments. When using stencil buffers, you can get as crazy as you like, but the general outline is usually as follows. Enable writing to the stencil buffer. Render objects, updating the content of the stencil buffer. Disable writing to the stencil buffer. Render other objects, this time discarding certain fragments based on the content of the stencil buffer. By using the stencil buffer, we can thus discard certain fragments based on the fragments of other drawn objects in the scene. You can enable stencil testing by enabling GL stencil test. From that point on, all rendering calls will influence the stencil buffer in one way or another. Note that you also need to clear the stencil buffer each iteration, just like the color and depth buffer.
I feel like to skip this chapter. It's like not very important, I guess. Blending.
Blending in OpenGL is commonly known as the technique to implement transparency within objects. Transparency is all about objects or parts of them not having a solid color, but having a combination of colors from the object itself and any other object behind it with varying intensity. A colored glass window is a transparent object. The glass has a color of its own, but the resulting color contains the colors of all the objects behind the glass as well. This is also where the name blending comes from, since we blend several pixel colors from different objects to a single color. Transparency thus allows us to see through objects. Transparent objects can be completely transparent, letting all colors through, or partially transparent, letting colors through, but also some of its own colors. The amount of transparency of an object is defined by its color's alpha value. The alpha color value is the fourth component of a color vector that you've probably seen quite often now. Up until this chapter, we've always kept this fourth component, a value of 1.0, giving the object 0.0 transparency. An alpha value of 0.0 would result in the object having complete transparency. An alpha value of 0.5 tells us the object's color consists of 50% of its own color and 50% of the colors behind the object. The textures we've used so far all consisted of 3 color components, red, green, and blue, but some textures also have an embedded alpha channel that contains an alpha value per texel. This alpha value tells us exactly which parts of the texture have transparency and by how much. For example, the window texture 1 below has an alpha value of 0.25 at its glass part and an alpha value of 0.0 at its corners. The glass part would normally be completely red, but since it has 75% transparency, it largely shows the page background through it, making it seem a lot less red. We'll soon be adding this windowed texture to the scene from the depth testing chapter, but first we'll discuss an easier technique to implement transparency for pixels that are either fully transparent or fully opaque. Discarding fragments, some effects do not care about partial transparency, but either want to show something or nothing at all based on the color value of a texture. Think of grass. To create something like grass with little effort, you generally paste a grass texture onto a 2D quad and place that quad into your scene. However, grass isn't exactly shaped like a 2D square, so you only want to display some parts of the grass texture and ignore the others. The grass texture 1 below is exactly such a texture where it either is full opaque, an alpha value of 1.0, or it is fully transparent, an alpha value of 0.0, and nothing in between. You can see that, wherever there is no grass, the image shows the paper's color instead of its own. So when adding vegetation to a scene, we don't want to see a square image of grass, but rather only show the actual grass and see through the rest of the image. We want to discard the fragments that show the transparent parts of the texture, not storing that fragment into the color buffer. Before we get into that, we first need to learn how to load a transparent texture. To load textures with alpha values, there's not much we need to change. STB image automatically loads an image's alpha channel if it's available, but we do need to tell OpenGL our texture now uses an alpha channel in the texture generation procedure. Also make sure that you retrieve all 4 color components of the texture in the fragment shader, not just the RGB components. Now that we know how to load transparent textures, it's time to put it to the test by adding several of these leaves of grass throughout the basic scene introduced in the depth testing chapter. We create a small vector array where we add several glm::vec3 vectors to represent the location of the grass leaves. Each of the grass objects is rendered as a single quad with the grass texture attached to it. It's not a perfect 3D representation of grass, but it's a lot more efficient than loading and rendering a large number of convex models. With a few tricks like adding randomized rotations and scales, you can get pretty convincing results with quads. Because the grass texture is going to be displayed on a quad object, we'll need to create another VBO again, fill the VBO, and set the appropriate vertex attribute pointers. Then, after we've rendered the floor and the 2 cubes, we're going to render the grass leaves. Running the application will now look a bit like this. This happens because OpenGL by default does not know what to do with alpha values, nor when to discard them. We have to manually do this ourselves. Luckily, this is quite easy thanks to the use of shaders. GLSL gives us the discard command that once called ensures the fragment will not be further processed and thus not end up into the color buffer. Thanks to this command, we can check whether a fragment has an alpha value below a certain threshold, and if so, discard the fragment as if it had never been processed.
Let me see if we do have discard. I don't think there is a discard. Yeah, I don't see. Oh, there is a discard. So we can do discard. Okay. So let's skip this chapter as well. Just speed running. Sub section, I guess.
While discarding fragments is great and all, it doesn't give us the flexibility to render semi-transparent images. We either render the fragment or completely discard it. To render images with different levels of transparency, we have to enable blending. Like most of OpenGL's functionality, we can enable blending by enabling GLBlend. Now that we've enabled blending, we need to tell OpenGL how it should actually blend. Blending in OpenGL happens with the following equation.
Source factor value, factor value. So f is alpha.
After the fragment shader has run and all the tests have passed, this blend equation is let loose on the fragment's color output and with whatever is currently in the color buffer. The source and destination colors will automatically be set by OpenGL, but the source and destination factor can be set to a value of our choosing. Let's start with a simple example. We have 2 squares where we want to draw the semi-transparent green square on top of the red square. The red square will be the destination color, and thus should be first in the color buffer, and we are now going to draw the green square over the red square. The question then arises, what do we set the factor values to? Well, we at least want to multiply the green square with its alpha value, so we want to set the FSRC equal to the alpha value of the source color vector, which is 0.6. Then it makes sense to let the destination square have a contribution equal to the remainder of the alpha value. If the green square contributes 60% to the final color, we want the red square to contribute 40% of the final color, e.g. 1.0, 0.6, so we set f destination equal to 1 minus the alpha value of the source color vector. The equation thus becomes the result is that the combined square fragments contain a color that is 60% green and 40% red. The resulting color is then stored in the color buffer, replacing the previous color. So this is great and all, but how do we actually tell OpenGL to use factors like that? Well, it just so happens that there's a function for this called glblendfunc. The glblendfunc factor, glnmd factor function expects 2 parameters that set the option for the source and destination factor. OpenGL defined quite a few options for us, to set of which we'll list the most common option below. Note that the constant color vector C constant can be separately set via the GL blend color function. To get the blending result of our little 2-square example, we want to take the alpha of the source color vector for the source factor and 1 minus alpha of the same color vector for the destination factor. This translates to GL blend func as follows. OpenGL gives us even more flexibility by allowing us to change the operator between the source and destination part of the equation. Right now, the source and destination components are added together, but we could also subtract them if we want. GL blend equation GLenim mode allows us to set this operation and has 5 possible options. Now that we know how OpenGL works with regards to blending, it's time to put our knowledge to the test, adding several semi-transparent windows. We'll be using the same scene as in the start of this chapter, but instead of rendering a grass texture, we're now going to use the transparent window texture from the start of this chapter. The reason for this is that depth testing works a bit tricky combined with blending. When writing to the depth buffer, the depth test does not care if the fragment has transparency or not, so the transparent parts are written to the depth buffer as any other value. The result is that the background windows are tested on depth as any other opaque object would be, ignoring transparency. Even though the transparent part should show the windows behind it, the depth test discards them. So we cannot simply render the windows however we want and expect the depth buffer to solve all our issues for us. This is also where blending gets a little nasty. To make sure the windows show the windows behind them, we have to draw the windows in the background first. This means we have to manually sort the windows from furthest to nearest and draw them accordingly ourselves. Note that with fully transparent objects like the grass leaves, we have the option to discard the transparent fragments instead of blending them, saving us a few of these headaches, no depth issues. Don't break the order to make blending work for multiple objects. We have to draw the most distant object first and the closest object last. The normal non-blended objects can still be drawn as normal using the depth buffer, so they don't have to be sorted. We do have to make sure they are drawn first before drawing the sorted transparent objects. When drawing a scene with non-transparent and transparent objects, the general outline is usually as follows. 1. Draw all opaque objects first. 2. Sort all the transparent objects. 3. Draw all the transparent objects in sorted order. One way of sorting the transparent objects is to retrieve the distance of an object from the viewer's perspective. This can be achieved by taking the distance between the camera's position vector and the object's position vector. We then store this distance together with the corresponding position vector in a map data structure from the SDL library. A map automatically sorts its values based on its keys, so once we've added all positions with their distance as the key, they're automatically sorted on their distance value. The result is a sorted container object that stores each of the window positions based on their distance key value from lowest to highest distance. Then, this time when rendering, we take each of the map's values in reverse order from farthest to nearest and then draw the corresponding windows in correct order. We take a reverse iterator from the map to iterate through each of the items in reverse order and then translate each window quad to the corresponding window position. This relatively simple approach to sorting transparent objects fixes the previous problem, and now the scene looks like this. You can find the complete source code with sorting at /src/4.advancedopengl/3.2 blending sort/. While this approach of sorting the objects by their distance works well for this specific scenario, it doesn't take rotations, scaling, or any other transformation into account, and weirdly shaped objects need a different metric than simply a position vector. Sorting objects in your scene is a difficult feat that depends greatly on the type of scene you have, let alone the extra processing power it costs. Completely rendering a scene with solid and transparent objects isn't all that easy. There are more advanced techniques like order-independent transparency, but these are out of the scope of this chapter. For now, you'll have to live with normally blending your objects, but if you're careful and know the limitations, you can get pretty decent blending implementations.
I'm wondering why it's called advanced. It's everything is just
Face culling, try mentally
not want
visualizing a
to
3D
run
cube
tests.
and count the maximum number of faces you'll be able to see from any direction. If your imagination is not too creative, you probably ended up with a maximum number of 3. You can view a cube from any position and / or direction, but you would never be able to see more than 3 faces. So why would we waste the effort of drawing those other 3 faces that we can't even see? If we could discard those in some way, we would save more than 50% of this cube's total fragment shader runs. We say more than 50% instead of 50% because from certain angles, only 2 or even 1 face could be visible. In that case, we'd save more than 50%. This is a really great idea, but there's one problem we need to solve. How do we know if a face of an object is not visible from the viewer's point of view? If we imagine any closed shape, each of its faces has two sides. Each side would either face the user or show its back to the user. What if we could only render the faces that are facing the viewer? This is exactly what face culling does. OpenGL checks all the faces that are front-facing towards the viewer and renders those while discarding all the faces that are back-facing, saving us a lot of fragment shader calls. We do need to tell OpenGL which of the faces we use are actually the front faces and which faces are the back faces. OpenGL uses a clever trick for this by analyzing the winding order of the vertex data. Winding order. When we define a set of triangle vertices, we're defining them in a certain winding order that is either clockwise or counterclockwise. Each triangle consists of 3 vertices, and we specify those 3 vertices in a winding order as seen from the center of the triangle. As you can see in the image, we first define vertex 1, and from there, we can choose whether the next vertex is 2 or 3. This choice defined the winding order of this triangle. The following code illustrates this.
Yeah, anyways, this is as well simple topic. Okay, frame buffers.
So far, we've used several types of screen buffers, a color buffer for writing color values, a depth buffer to write and test depth information, and finally, a stencil buffer that allows us to discard certain fragments based on some condition. The combination of these buffers is stored somewhere in GPU memory and is called a frame buffer. OpenGL gives us the flexibility to define our own frame buffers and thus define our own color and optionally a depth and stencil buffer. The rendering operations we've done so far were all done on top of the render buffers attached to the default frame buffer. The default frame buffer is created and configured when you create your window GLFW distance for us.
Discord.
By creating our own frame buffer, we can get an additional target to render to. The application of frame buffers may not immediately make sense, but rendering your scene to a different frame buffer allows us to use that result to create mirrors in a scene or do cool post-processing effects, for example. First, we'll discuss how they actually work, and then we'll use them by implementing those cool post-processing effects.
Streamer mode. Enable streaming mode. Creating frame buffers. Yeah, so I need to use different API for creating and having access to frame buffers. And I think there is a example. I think I did see examples which doing frame buffers.
Now that the entire scene is rendered to a single texture, we can create cool post-processing effects by manipulating the scene texture. In this section, we'll show you some of the more popular post-processing effects and how you may create your own with some added creativity. We have access to each of the colors of the render output, so it's not so hard to return the inverse of these colors in the fragment shader. We can take the color of the screen texture and inverse it by subtracting it from 1.0.
Grayscale. Kernel effects.
Another advantage about doing post-processing on a single texture image is that we can sample color values from other parts of the texture, not specific to that fragment.
Blur.
We could, for example, take a small area around the current texture coordinate and sample multiple texture values around the current texture value. We can then create interesting effects by combining them in creative ways. A kernel or convolution matrix is a small matrix-like array of values centered on the current pixel that multiplies surrounding pixel values by its kernel values and adds them all together to form a single value. We're adding a small offset to the texture coordinates in surrounding directions of the current pixel and combine the results based on the kernel. An example of a kernel is given below.
Cube maps.
Cube maps, we've been using 2D textures for a while now, but there are more texture types we haven't explored yet, and in this chapter, we'll discuss a texture type that is a combination of multiple textures mapped into one, a cube map. A cube map is a texture that contains 6 individual 2D textures that each form one side of a cube, a textured cube. You may be wondering what the point is of such a cube. Why bother combining 6 individual textures into a single entity instead of just using 6 individual textures? Well, cube maps have the useful property that they can be indexed/sampled using a direction vector. Imagine we have a 1x1x1 unit cube with the origin of a direction vector residing at its center. Sampling a texture value from the cube map with an orange direction vector looks a bit like this.
Okay, I don't know. Yeah, this is for skybox, right? For skyboxes. environment mapping.
We now have the entire surrounding environment mapped in a single texture object, and we could use that information for more than just a skybox. Using a cube map with an environment, we could give objects reflective or refractive properties. Techniques that use an environment cube map like this are called environment mapping techniques, and the two most popular ones are reflection and refraction. Reflection is the property that an object or part of an object reflects its surrounding environment, e.g. the object's colors are more or less equal to its environment based on the angle of the viewer. A mirror, for example, is a reflective object. It reflects its surroundings based on the viewer's angle. The basics of reflection are not that difficult. The following image shows how we can calculate a reflection vector and use that vector to sample from a cube map.
Oh, that's interesting. I guess we can try to implement
We calculate
it.
a reflection vector r around the object's normal vector, n based on the view direction vector I. We can calculate this reflection vector using GLSL built-in reflect function. The resulting vector r is then used as a direction vector to index/sample the cube map, returning a color value of the environment. The resulting effect is that the objects seem to reflect the skybox. Since we already have a skybox set up in our scene, creating reflections isn't too difficult. We'll change the fragment shader used by the container to give the container reflective properties.
Built-in variables. I'm having like a urge to skim through all this stuff. Geometry shaders. Okay, so yeah, we between there's a fragment shader, there is optional shader stage called geometry shader. Oh, instancing. So instancing is the essential idea of geometry shader.
Say you have a scene where you're drawing a lot of models where most of these models contain the same set of vertex data but with different world transformations. Think of a scene filled with grass leaves. Each grass leaf is a small model that consists of only a few triangles. You'll probably want to draw quite a few of them, and your scene may end up with thousands or maybe tens of thousands of grass leaves that you need to render each frame. Because each leaf is only a few triangles, the leaf is rendered almost instantly. However, the thousands of render calls you'll have to make will drastically reduce performance. If we were to actually render such a large amount of objects, it will look a bit like this in code. When drawing many instances of your model like this, you'll quickly reach a performance bottleneck because of the many draw calls. Compared to rendering the actual vertices, telling the GPU to render your vertex data with functions like glDrawArrays or glDrawElements eats up quite some performance, since OpenGL must make necessary preparations before it can draw your vertex data, like telling the GPU which buffer to read data from, where to find vertex attributes, and all this over the relatively slow CPU to GPU bus. So even though rendering your vertices is super fast, giving your GPU the commands to render them isn't. It would be much more convenient if we could send data over to the GPU once, and then tell OpenGL to draw multiple objects using this data with a single drawing call. Enter instancing. Instancing is a technique where we draw many equal mesh data objects at once with a single render call, saving us all the CPU-GPU communications each time we need to render an object. To render using instancing, all we need to do is change the render calls glDrawArrays and glDrawElements to glDrawArrays instanced and glDrawElements instanced respectively. These instant versions of the classic rendering functions take an extra parameter called the instance count that set the number of instances we want to render. We sent all the required data to the GPU once, and then tell the GPU how it should draw all these instances with a single call. The GPU then renders all these instances without having to continually communicate with the CPU. By itself, this function is a bit useless. Rendering the same object 1,000 times is of no use to us, since each of the rendered objects is rendered exactly the same, and thus also at the same location. We would only see one object. For this reason, GLSL added another built-in variable in the vertex shader called GLInstanceID. When drawing with one of the instance rendering calls, GLInstanceID is incremented for each instance being rendered starting from 0. If we were to render the 43rd instance, for example, GLInstanceID would have the value 42 in the vertex shader. Having a unique value per instance means we could now, for example, index into a large array of position values to position each instance at a different location in the world. To get a feel for instance drawing, we're going to demonstrate a simple example that renders 100 2D quads in normalized device coordinates with just one render call. We accomplish this by uniquely positioning each instance quad by indexing a uniform array of 100 offset vectors. The result is a neatly organized grid of quads that fill the entire window.
Anti-aliasing. Interesting. Why we are talking about anti-aliasing?
Somewhere in your adventurous rendering journey, you probably came across some jagged saw-like patterns along the edges of your models. The reason these jagged edges appear is due to how the rasterizer transformed the vertex data into actual fragments behind the scene. An example of what these jagged edges look like can already be seen when drawing a simple cube. This is clearly not something we want in a final version of an application. This effect of clearly seeing the pixel formations an edge is composed of is called aliasing. There are quite a few techniques out there called anti-aliasing techniques that fight this aliasing behavior by producing smoother edges. At first, we had a technique called supersample anti-aliasing SAW that temporarily uses a much higher resolution render buffer to render the scene in supersampling. Then, when the full scene is rendered, the resolution is downsampled back to the normal resolution. This extra resolution was used to prevent these jagged edges. While it did provide us with a solution to the aliasing problem, it came with a major performance drawback since we have to draw a lot more fragments than usual. This technique therefore only had a short glory moment. This technique did give birth to a more modern technique called multisample anti-aliasing, or MSAA, that borrows from the concepts behind SAW while implementing a much more efficient approach. In this chapter, we'll be extensively discussing this MSAA technique that is built in OpenGL. Multisampling. To understand what multisampling is and how it works into solving the aliasing problem, we first need to delve a bit further into the inner workings of OpenGL's rasterizer. The rasterizer is the combination of all algorithms and processes that sit between your final processed vertices and the fragment shader. The rasterizer takes all vertices belonging to a single primitive and transforms this to a set of fragments. Vertex coordinates can theoretically have any coordinate, but fragments can't since they are bound by the resolution of your screen. There will almost never be a one-on-one mapping between vertex coordinates and fragments, so the rasterizer has to determine in some way what fragment/screen coordinate each specific vertex will end up at. Here we see a grid of screen pixels where the center of each pixel contains a sample point that is used to determine if a pixel is covered by the triangle. The red sample points are covered by the triangle, and a fragment will be generated for that covered pixel. Even though some parts of the triangle edges still enter certain screen pixels, the pixel's sample point is not covered by the inside of the triangle, so this pixel won't be influenced by any fragment shader. You can probably already figure out the origin of aliasing right now. The complete rendered version of the triangle would look like this on your screen. Due to the limited amount of screen pixels, some pixels will be rendered along an edge and some won't. The result is that we're rendering primitives with non-smooth edges, giving rise to the jagged edges we've seen before. What multisampling does is not use a single sampling point for determining coverage of the triangle, but multiple sample points guess where it got its name from. Instead of a single sample point at the center of each pixel, we're going to place 4 subsamples in a general pattern and use those to determine pixel coverage. The left side of the image shows how we would normally determine the coverage of a triangle. This specific pixel won't run a fragment shader and thus remains blank since its sample point wasn't covered by the triangle. The right side of the image shows a multi-sampled version where each pixel contains 4 sample points. Here we can see that only 2 of the sample points cover the triangle. The amount of sample points can be any number we'd like, with more samples giving us better coverage precision. This is where multisampling becomes interesting. We determined that 2 subsamples were covered by the triangle, so the next step is to determine a color for this specific pixel. Our initial guess would be that we run the fragment shader for each covered subsample and later average the colors of each subsample per pixel. In this case, we'd run the fragment shader twice on the interpolated vertex data at each subsample and store the resulting color in those sample points. This is fortunately not how it works, because this would mean we need to run a lot more fragment shaders than without multisampling, drastically reducing performance. How MSAA really works is that the fragment shader is only run once per pixel for each primitive, regardless of how many subsamples the triangle covers. The fragment shader runs with the vertex data interpolated to the center of the pixel. MSAA then uses a much larger depth /stencil not color buffer to determine subsample coverage. The number of subsamples covered determines how much the pixel color contributes to the frame buffer. Because only 2 of the 4 samples were covered in the previous image, half of the triangle's color is mixed with the frame buffer color, in this case, the clear color, resulting in a light bluish color. The result is a higher resolution buffer with higher resolution depth /stencil, where all the primitive edges now produce a smoother pattern. Let's see what multisampling looks like when we determine the coverage of the earlier triangle. Here, each pixel contains 4 subsamples. The irrelevant samples were hidden where the blue subsamples are covered by the triangle, and the gray sample points aren't. Within the inner region of the triangle, all pixels will run the fragment shader, once where its color output is stored directly in the frame buffer, assuming no blending. At the inner edges of the triangle, however, not all subsamples will be covered, so the result of the fragment shader won't fully contribute to the frame buffer. Based on the number of covered samples, more or less of the triangle fragment's color ends up at that pixel.
Anyways, I think I will skip this portion as well. This is needed, but we can focus on it, then we will need it. Right. Advanced lighting. Advanced lighting.
In the lighting chapters, we briefly introduced the Phong lighting model to bring a basic amount of realism into our scenes. The Phong model looks nice, but has a few nuances we'll focus on in this chapter. Blint Phong lighting is a great and very efficient approximation of lighting, but its specular reflections break down in certain conditions, specifically when the shininess property is low, resulting in a large rough specular area. The image below shows what happens when we use a specular shininess exponent of 1.0 on a flat textured plane. You can see at the edges that the specular area is immediately cut off. The reason this happens is because the angle between the view and reflection vector doesn't go over 90 degrees. If the angle is larger than 90 degrees, the resultant dot product becomes negative, and this results in a specular exponent of 0.0. You're probably thinking this won't be a problem, since we shouldn't get any light with angles higher than 90 degrees anyways, right? Wrong. This only applies to the diffuse component, where an angle higher than 90 degrees between the normal and light source means the light source is below the lighted surface, and thus the light diffuse contribution should equal 0.0. However, with specular lighting, we're not measuring the angle between the light source and the normal, but between the view and reflection vector. Take a look at the following 2 images. In 1977, the Blinn-Phong shading model was introduced by James F. Blinn as an extension to the Phong shading we've used so far. The Blinn-Phong model is largely similar, but approaches the specular model slightly different, which as a result overcomes our problem. Instead of relying on a reflection vector, we're using a so-called halfway vector that is a unit vector exactly halfway between the view direction and the light direction. The closer this halfway vector aligns with the surface's normal vector, the higher the specular contribution.
Okay, so it's calculating specular value with new formula, gamma correction, not interesting, it's all technicality, attenuation.
Something else that's different with gamma correction is lighting attenuation. In the real physical world, lighting attenuates closely inversely proportional to the squared distance from a light source. In normal English, it simply means that the light strength is reduced over the distance to the light source squared, like below. However, when using this equation, the attenuation effect is usually way too strong, giving lights a small radius that doesn't look physically right. For that reason, other attenuation functions were used like we discussed in the basic lighting chapter that give much more control, or the linear equivalent is used. The linear equivalent gives more plausible results compared to its quadratic variant without gamma correction. But when we enable gamma correction, the linear attenuation looks too weak, and the physically correct quadratic attenuation suddenly gives the better results. The image below shows the differences.
Ah, interesting.
The cause of this difference is that light attenuation functions change brightness, and as we weren't visualizing our scene in linear space, we chose the attenuation functions that look best on our monitor, but weren't physically correct. Think of the squared attenuation function. If we were to use this function without gamma correction, the attenuation function effectively becomes 1.0/distance 2.2 when displayed on a monitor. This creates a much larger attenuation from what we originally anticipated. This also explains why the linear equivalent makes much more sense without gamma correction, as this effectively becomes 1.0/distance 2.2 equals 1.0/distance 2.2, which resembles its physical equivalent a lot more. The more advanced attenuation function we discussed in the basic lighting chapter still has its place in gamma-corrected scenes, as it gives more control over the exact attenuation, but of course requires different parameters in a gamma-corrected scene. You can find the source code of this simple demo seen at /src/5.advancedlighting/2.gammacorrection/. By pressing the
Shadow
spacebar,
mapping.
we switch between a gamma-corrected and uncorrected scene, with both scenes using their texture and attenuation equivalents. It's not the most impressive demo, but it does show how to actually apply all techniques. To summarize, gamma correction allows us to do all our shader/lighting calculations in linear space. Because linear space makes sense in the physical world, most physical equations now actually give good results like real light attenuation. The more advanced your lighting becomes, the easier it is to get good-looking and realistic results with gamma correction. That is also why it's advised to only really tweak your lighting parameters as soon as you have gamma correction in place. Shadow mapping shadows are a result of the absence of light due to occlusion. When a light source's light rays do not hit an object, because it gets occluded by some other object, the object is in shadow. Shadows add a great deal of realism to a lit scene and make it easier for a viewer to observe spatial relationships between objects. They give a greater sense of depth to our scene and objects. For example, take a look at the following image of a scene with and without shadows. You can see that with shadows, it becomes much more obvious how the objects relate to each other. For instance, the fact that one of the cubes is floating above the others is only really noticeable when we have shadows. Shadows are a bit tricky to implement though, specifically because in current real-time rasterized graphics, research a perfect shadow algorithm hasn't been developed yet. There are several good shadow approximation techniques, but they all have their little quirks and annoyances, which we have to take into account. One technique used by most video games that gives decent results and is relatively easy to implement is shadow mapping. Shadow mapping is not too difficult to understand, doesn't cost too much in performance, and quite easily extends into more advanced algorithms like omnidirectional shadow maps and cascaded shadow maps. Shadow mapping. The idea behind shadow mapping is quite simple. We render the scene from the light's point of view, and everything we see from the light's perspective is lit, and everything we can't see must be in shadow. Imagine a floor section with a large box between itself and a light source. Since the light source will see this box, and not the floor section when looking in its direction, that specific floor section should be in shadow. Here, all the blue lines represent the fragments that the light source can see. The occluded fragments are shown as black lines. These are rendered as being shadowed. If we were to draw a line or ray from the light source to a fragment on the rightmost box, we can see the ray first hits. The floating container before hitting the rightmost container. As a result, the floating container's fragment is lit, and the rightmost container's fragment is not lit and thus in shadow. We want to get the point on the ray where it first hit an object and compare this closest point to other points on this ray. We then do a basic test to see if a test point's ray position is further down the ray than the closest point, and if so, the test point must be in shadow. Iterating through possibly thousands of light rays from such a light source is an extremely inefficient approach and doesn't lend itself too well for real-time rendering. We can do something similar, but without casting light rays. Instead, we use something we're quite familiar with, the depth buffer. You may remember from the depth testing chapter that a value in the depth buffer corresponds to the depth of a fragment clamped to 0, 1 from the camera's point of view. What if we were to render the scene from the light perspective and store the resulting depth values in a texture? This way, we can sample the closest depth values as seen from the light perspective. After all, the depth values show the first fragment visible from the light's perspective. We store all these depth values in a texture that we call a depth map or shadow map. The left image shows a directional light source. All light rays are parallel, casting a shadow on the surface below the cube. Using the depth values stored in the depth map, we find the closest point in use to determine whether fragments are in shadow. We create the depth map by rendering the scene from the light's perspective using a view and projection matrix specific to that light source. This projection and view matrix together form a transformation T that transforms any 3D position to the light's visible coordinate space. A directional light doesn't have a position, as it's modeled to be infinitely far away. However, for the sake of shadow mapping, we need to render the scene from a light perspective, and thus render the scene from a position somewhere along the lines of the light direction. In the right image, we see the same directional light and the viewer. We render a fragment at point P, for which we have to determine whether it is in shadow. To do this, we first transform point P to the light's coordinate space using T. Since point P is now as seen from the light's perspective, its z-coordinate corresponds to its depth, which in this example is 0.9. Using point P, we can also index the depth/shadow map to obtain the closest visible depth from the light's perspective, which is at point C with a sampled depth of 0.4. Since indexing the depth map returns a depth smaller than the depth at point P, we can conclude point P is occluded and thus in shadow.
I guess I kind of get the idea. Did I get the idea? I do not know if I get the idea. I'm wondering why sometimes my camera is freezing and sometimes it's working fine. Point shadows. PSF. Normal mapping. This is just altering. This is the very simple thing. Normals are super simple to implement, so we are going to skip. It's probably need to pay a little bit more attention to shadows, but I think idea is kind of you create the texture, shadow texture, draw the shadow, and then you use it. Parallax mapping. Parallax mapping technique similar to normal mapping, but based on
Parallax mapping is a technique similar to neural mapping, but based on different principles. Just like neural mapping, it is a technique that significantly boosts a textured surface's detail and gives it a sense of depth. While also an illusion, parallax mapping is a lot better in conveying a sense of depth, and together with neural mapping gives incredibly realistic results. While parallax mapping isn't necessarily a technique directly related to advanced lighting, I'll still discuss it here as the technique is a logical follow-up of neural mapping. Note that getting an understanding of neural mapping, specifically tangent space, is strongly advised before learning parallax mapping. Parallax mapping is closely related to the family of displacement mapping techniques that displace or offset vertices based on geometrical information stored inside a texture. One way to do this is to take a plane with roughly 1,000 vertices and displace each of these vertices based on a value in a texture that tells us the height of the plane at that specific area. Such a texture that contains height values per pixel is called a height map. An example height map, derived from the geometric properties of a simple brick surface, looks a bit like this. When spanned over a plane, each vertex is displaced based on the sampled height value in the height map, transforming a flat plane to a rough, bumpy surface based on a material's geometric properties. For instance, taking a flat plane displaced with the above height map results in the following image. The problem with displacing vertices this way is that a plane needs to contain a huge amount of triangles to get a realistic displacement, otherwise the displacement looks too blocky. As each flat surface may then require over 10,000 vertices, this quickly becomes computationally infeasible. What if we could somehow achieve similar realism without the need of extra vertices? In fact, what if I were to tell you that the previously shown displaced surface is actually rendered with only 2 triangles? This brick surface shown is rendered with parallax mapping, a displacement mapping technique that doesn't require extra vertex data to convey depth, but similar to neural mapping, uses a clever technique to trick the user. The idea behind parallax mapping is to alter the texture coordinates in such a way that it looks like a fragment surface is higher or lower than it actually is, all based on the view direction and a height map. To understand how it works, take a look at the following image of our brick surface.
Yeah, I saw this thing. I guess. Oh yeah. And I saw this thing. HDR.
Brightness and color values by default are clamped between 0.0 and 1.0 when stored into a frame buffer. This, at first seemingly innocent, statement caused us to always specify light and color values somewhere in this range, trying to make them fit into the scene. This works okay and gives decent results, but what happens if we walk in a really bright area with multiple bright light sources that as a total sum exceed 1.0? The answer is that all fragments that have a brightness or color sum over 1.0 get clamped to 1.0, which isn't pretty to look at. Due to a large number of fragments' color values getting clamped to 1.0, each of the bright fragments have the exact same white color value in large regions, losing a significant amount of detail and giving it a fake look. A solution to this problem would be to reduce the strength of the light sources and ensure no area of fragments in your scene ends up brighter than 1.0. This is not a good solution, as this forces you to use unrealistic lighting parameters. The better approach is to allow color values to temporarily exceed 1.0 and transform them back to the original range of 0.0 and 1.0 as a final step, but without losing detail. Monitors non-HDR are limited to display colors in the range of 0.0 and 1.0, but there is no such limitation in lighting equations. By allowing fragment colors to exceed 1.0, we have a much higher range of color values available to work in known as high dynamic range HDR. With high dynamic range, bright things can be really bright, dark things can be really dark, and details can be seen in both. High dynamic range was originally only used for photography, where a photographer takes multiple pictures of the same scene with varying exposure levels, capturing a large range of color values. Combining these forms a HDR image where a large range of details are visible based on the combined exposure levels, or a specific exposure it is viewed with. For instance, the following image credits to Colin Smith shows a lot of detail at brightly lit regions with a low exposure look at the window, but these details are gone with a high exposure. However, a high exposure now reveals a great amount of detail at darker regions that weren't previously visible. This is also very similar to how the human eye works and the basis of high dynamic range rendering. When there's little light, the human eye adapts itself so the darker parts become more visible, and similarly for bright areas. It's like the human eye has an automatic exposure slider based on the scene brightness. High dynamic range rendering works a bit like that. We allow for a much larger range of color values to render to, collecting a large range of dark and bright details of scene, and at the end, we transform all the HDR values back to the low dynamic range LDR of 0.0, 1.0. This process of converting HDR values to LDR values is called tone mapping, and a large collection of tone mapping algorithms exist that aim to preserve most HDR details during the conversion process. These tone mapping algorithms often involve an exposure parameter that selectively favors dark or bright regions. When it comes to real-time rendering, high dynamic range allows us to not only exceed the LDR range of 0.0, 1.0, and preserve more detail, but also gives us the ability to specify a light source's intensity by their real intensities. For instance, the sun has a much higher intensity than something like a flashlight, so why not configure the sun as such, e.g. a diffuse brightness of 100.0. This allows us to more properly configure scenes, lighting with more realistic lighting parameters, something that wouldn't be possible with LDR rendering, as they then directly get clamped to 1.0. As non-HDR monitors only display colors in the range between 0.0 and 1.0, we do need to transform the currently high dynamic range of color values back to the monitor's range. Simply retransforming the colors back with a simple average wouldn't do us much good, as brighter areas then become a lot more dominant. What we can do is use different equations and slash or curves to transform the HDR values back to LDR that give us complete control over the scene brightness. This is the process earlier denoted as tone mapping and the final step of HDR rendering.
Skipping tone mapping. Bloom.
Bright light sources and brightly lit regions are often difficult to convey to the viewer, as the intensity range of monitor is limited. One way to distinguish bright light sources on a monitor is by making them glow. The light then bleeds around the light source. This effectively gives the viewer the illusion these light sources or bright regions are intensely bright. This light bleeding or glow effect is achieved with a post-processing effect called bloom. Bloom gives all brightly lit regions of a scene a glow-like effect. An example of a scene with and without glow can be seen below image, courtesy of EP Games. Bloom gives notable visual cues about the brightness of objects. When done in a subtle fashion, which some games drastically fail to do, bloom significantly boosts the lighting of your scene and allows for a large range of dramatic effects. Bloom works best in combination with HDR rendering. A common misconception is that HDR is the same as bloom, as many people use the terms interchangeably. They are, however, completely different techniques, used for different purposes. It is possible to implement bloom with default 8-bit precision frame buffers, just as it is possible to use HDR without the bloom effect. It is simply that HDR makes bloom more effective to implement, as we'll later see. To implement bloom, we render a lit scene as usual and extract both the scene's HDR color buffer and an image of the scene with only its bright regions visible. This extracted brightness image is then blurred, and the result added on top of the original HDR scene image. Let's illustrate the process in a step-by-step fashion. We render a scene filled with 4 bright light sources, visualized as colored cubes. The colored light cubes have a brightness values between 1.5 and 15.0. If we were to render this to an HDR color buffer, the scene looks as follows.
Deferred shading. What is this?
Deferred shading, the way we did lighting so far, was called forward rendering or forward shading, a straightforward approach where we render an object and light it according to all light sources in a scene. We do this for every object individually, for each object in the scene. While quite easy to understand and implement, it is also quite heavy on performance, as each rendered object has to iterate over each light source for every rendered fragment, which is a lot. Forward rendering also tends to waste a lot of fragment shader runs in scenes with a high depth complexity. Multiple objects cover the same screen pixel, as fragment shader outputs are overwritten. Deferred shading or deferred rendering aims to overcome these issues by drastically changing the way we render objects. This gives us several new options to significantly optimize scenes with large numbers of lights, allowing us to render hundreds or even thousands of lights with an acceptable frame rate. The following image is a scene with 1,847 point lights, rendered with deferred shading image courtesy of Hans Nevalainen, something that wouldn't be possible with forward rendering. Deferred shading is based on the idea that we defer or postpone most of the heavy rendering, like lighting, to a later stage. Deferred shading consists of 2 passes. In the first pass, called the geometry pass, we render the scene once and retrieve all kinds of geometrical information from the objects that we store in a collection of textures called the G buffer. Think of position vectors, color vectors, normal vectors, and slash or specular values. The geometric information of a scene stored in the G buffer is then later used for more complex lighting calculations. Below is the content of a G buffer of a single frame.
Position, normals, albedo, specular.
We use the textures from the G buffer in a second pass called the lighting pass, where we render a screen-filled quad and calculate the scene's lighting for each fragment using the geometrical information stored in the G buffer. Pixel by pixel, we iterate over the G buffer. Instead of taking each object all the way from the vertex shader to the fragment shader, we decouple its advanced fragment processes to a later stage. The lighting calculations are exactly the same, but this time we take all required input variables from the corresponding G buffer textures instead of the vertex shader plus some uniform variables. The image below nicely illustrates the process of deferred shading. A major advantage of this approach is that whatever fragment ends up in the G buffer is the actual fragment information that ends up as a screen pixel. The depth test already concluded this fragment to be the last and topmost fragment. This ensures that for each pixel we process in the lighting pass, we only calculate lighting once. Furthermore, deferred rendering opens up the possibility for further optimizations that allow us to render a much larger amount of light sources compared to forward rendering. It also comes with some disadvantages, though, as the G-buffer requires us to store a relatively large amount of scene data in its texture color buffers. This eats memory, especially since scene data like position vectors require a high precision. Another disadvantage is that it doesn't support blending, as we only have information of the topmost fragment, and MSA no longer works. There are several workarounds for this that we'll get to at the end of the chapter. Filling the G-buffer in the geometry pass isn't too expensive, as we directly store object information like position, color, or normals into a frame buffer with a small or zero amount of processing. By using multiple render targets, MRT, we can even do all of this in a single render pass. The G-buffer is the collective term of all textures used to store lighting-relevant data for the final lighting pass. Let's take this moment to briefly review all the data we need to light a fragment with forward rendering. A 3D world space position vector to calculate the interpolated fragment position variable used for light dyer and view dyer. An RGB diffuse color vector, also known as albedo. A 3D normal vector for determining a surface's slope. A specular intensity float, all light source position and color vectors. The player or viewer's position vector. With these fragment variables at our disposal, we are able to calculate the blend-fong lighting we're accustomed to. The light source positions and colors and the player's view position can be configured using uniform variables, but the other variables are all fragment-specific. If we can somehow pass the exact same data to the final deferred lighting pass, we can calculate the same lighting effects, even though we're rendering fragments of a 2D quad. There's no limit in OpenGL to what we can store in a texture, so it makes sense to store all per fragment data in one or multiple screen-filled textures of the G-buffer, and use these later in the lighting pass. As the G-buffer textures will have the same size as the lighting pass's 2D quad, we get the exact same fragment data we'd had in a forward rendering setting, but this time in the lighting pass, there's a one-on-one mapping. In pseudocode, the entire process will look a bit like this. The data we'll need to store of each fragment is a position vector, a normal vector, a color vector, and a specular intensity value. In the geometry pass, we need to render all objects of the scene and store these data components in the G-buffer. We can again use multiple render targets to render to multiple color buffers in a single render pass. This was briefly discussed in the Bloom chapter. With the geometry pass, we'll need to initialize a frame buffer object that we'll call G-buffer that has multiple color buffers attached and a single depth render buffer object. For the position and normal texture, we'd probably use a high precision texture 16 or 32-bit float per component. For the albedo and specular values, we'll be fine with the default texture precision, 8-bit precision per component. Note that we use GL-RGBA16F over GL-RGB16F, as GPUs generally prefer 4-component formats over 3-component formats due to byte alignment. Some drivers may fail to complete the frame buffer otherwise. Since we use multiple render targets, we have to explicitly tell OpenGL which of the color buffers associated with G-buffer we'd like to render to with GL draw buffers. Also interesting to note here is we combine the color and specular intensity data in a single RGBA texture. This saves us from having to declare an additional color buffer texture. As your deferred shading pipeline gets more complex and needs more data, you'll quickly find new ways to combine data in individual textures. Next, we need to render into the G-buffer. Assuming each object has a diffuse, normal, and specular texture, we'd use something like the following fragment shader to render into the G-buffer. The deferred lighting pass with a large collection of fragment data in the G-buffer at our disposal, we have the option to completely calculate the scene's final lit colors. We do this by iterating over each of the G-buffer textures, pixel by pixel, and use their content as input to the lighting algorithms. Because the G-buffer texture values all represent the final transformed fragment values, we only have to do the expensive lighting operations once per pixel. This is especially useful in complex scenes where we'd easily invoke multiple expensive fragment shader calls per pixel in a forward rendering setting. The lighting pass, we're going to render a 2D screen-filled quad, a bit like a post-processing. We bind all relevant textures of the G-buffer before rendering, and also send the lighting-relevant uniform variables to the shader. The fragment shader of the lighting pass is largely similar to the lighting chapter shaders we've used so far. What is new is the method in which we obtain the lighting's input variables, which we now directly sample from the G-buffer. The lighting pass shader accepts 3 uniform textures that represent the G-buffer and hold all the data we've stored in the geometry pass. If we were to sample these with the current fragment's texture coordinates, we get the exact same fragment values as if we were rendering the geometry directly. Note that we retrieve both the albedo color and the specular intensity from the single G albedo spec texture. As we now have the per fragment variables and the relevant uniform variables necessary to calculate blend-fong lighting, we don't have to make any changes to the lighting code. The only thing we change in deferred shading here is the method of obtaining lighting input variables. Running a simple demo with a total of 32 small lights looks a bit like this. One of the disadvantages of deferred shading is that it is not possible to do blending, as all values in the G-buffer are from single fragments, and blending operates on the combination of multiple fragments. Another disadvantage is that deferred shading forces you to use the same lighting algorithm for most of your scene's lighting. You can somehow alleviate this a bit by including more material-specific data in the G-buffer. To overcome these disadvantages, especially blending, we often split the renderer into 2 parts, one deferred rendering part, and the other, a forward rendering part specifically meant for blending or special shader effects not suited for a deferred rendering pipeline. To illustrate how this works, we'll render the light sources as small cubes using a forward renderer. As the light cubes require a special shader, simply output a single light color. Deferred rendering vs forward rendering by itself, without light volumes. Deferred shading is a nice optimization, as each pixel only runs a single fragment shader, compared to forward rendering, where we'd often run the fragment shader multiple times per pixel. Deferred rendering does come with a few disadvantages though: a large memory overhead, no MSAA, and blending still has to be done with forward rendering. When you have a small scene, and not too many lights, deferred rendering is not necessarily faster, and sometimes even slower, as the overhead then outweighs the benefits of deferred rendering. In more complex scenes, deferred rendering quickly becomes a significant optimization, especially with the more advanced optimization extensions. In addition, some render effects, especially post-processing effects, become cheaper on a deferred render pipeline, as a lot of scene inputs are already available from the gbuffer. As a final note, I'd like to mention that basically all effects that can be accomplished with forward rendering can also be implemented in a deferred rendering context. This often only requires a small translation step. For instance, if we want to use normal mapping in a deferred renderer, we change the geometry path shaders to output a world space normal extracted from a normal map using a TBN matrix instead of the surface normal. The lighting calculations and the lighting paths don't need to change at all. And if you want parallax mapping to work, you'd want to first displace the texture coordinates in the geometry paths before sampling in objects diffuse, specular, and normal textures. Once you understand the idea behind deferred rendering, it's not too difficult to get creative.
What is this? Ambient occlusion.
We've briefly touched the topic in the basic lighting chapter. Ambient lighting. Ambient lighting is a fixed light constant we add to the overall lighting of a scene to simulate the scattering of light. In reality, light scatters in all kinds of directions with varying intensities, so the indirectly lit parts of a scene should also have varying intensities. One type of indirect lighting approximation is called ambient occlusion, that tries to approximate indirect lighting by darkening creases, holes, and surfaces that are close to each other. These areas are largely occluded by surrounding geometry, and thus light rays have fewer places to escape to, hence the areas appear darker. Take a look at the corners and creases of your room to see that the light there seems just a little darker. Below is an example image of a scene with and without ambient occlusion. Notice how, especially between the creases, the ambient light is more occluded. While not an incredibly obvious effect, the image with ambient occlusion enabled does feel a lot more realistic due to these small occlusion-like details, giving the entire scene a greater feel of depth. Ambient occlusion techniques are expensive, as they have to take surrounding geometry into account. One could shoot a large number of rays for each point in space to determine its amount of occlusion, but that quickly becomes computationally infeasible for real-time solutions. In 2007, Crytek published a technique called screen space ambient occlusion (SSAO) for use in their title crises. The technique uses a scene's depth buffer in screen space to determine the amount of occlusion instead of real geometrical data. This approach is incredibly fast compared to real ambient occlusion and gives plausible results, making it the de facto standard for approximating real-time ambient occlusion. The basics behind screen space ambient occlusion are simple. For each fragment on a screenfilled quad, we calculate an occlusion factor based on the fragment's surrounding depth values. The occlusion factor is then used to reduce or nullify the fragment's ambient lighting component. The occlusion factor is obtained by taking multiple depth samples in a sphere sample kernel surrounding the fragment position and compare each of the samples with the current fragment's depth value. The number of samples that have a higher depth value than the fragment's depth represents the occlusion factor. Each of the gray depth samples that are inside geometry contribute to the total occlusion factor. The more samples we find inside geometry, the less ambient lighting the fragment should eventually receive. It is clear the quality and precision of the effect directly relates to the number of surrounding samples we take. If the sample count is too low, the precision drastically reduces, and we get an artifact called banding. If it is too high, we lose performance. We can reduce the amount of samples we have to test by introducing some randomness into the sample kernel. By randomly rotating the sample kernel, each fragment we can get high-quality results with a much smaller amount of samples. This does come at price, as the randomness introduces a noticeable noise pattern that we'll have to fix by blurring the results. Below is an image courtesy of johnchapmangraphicsblogspot.com/ showcasing the banding effect and the effect randomness has on the results.
Low sample banding, random rotation, noise, plus blur. This is not bad.
As you can see, even though we get notable banding on the SSAO results due to a low sample count, by introducing some randomness, the banding effects are completely gone. The SSAO method developed by Crytek had a certain visual style. Because the sample kernel used was sphere, it caused flat walls to look gray, as half of the kernel samples end up being in the surrounding geometry. Below is an image of Crysis's screen space ambient occlusion that clearly portrays this gray feel. For that reason, we won't be using a sphere sample kernel, but rather a hemisphere sample kernel oriented along a surface's normal vector. By sampling around this normal-oriented hemisphere, we do not consider the fragment's underlying geometry to be a contribution to the occlusion factor. This removes the gray feel of ambient occlusion and generally produces more realistic results. This chapter's technique is based on this normal-oriented hemisphere method and a slightly modified version of John Chapman's brilliant SSAO tutorial 1. Sample buffers SSAO requires geometrical info, as we need some way to determine the occlusion factor of a fragment. For each fragment, we're going to need the following data: a per fragment position vector, per fragment normal vector, per fragment albedo color, a sample kernel, a per fragment random rotation vector used to rotate the sample kernel. Using a per fragment view space position, we can orient a sample hemisphere kernel around the fragment's view space surface normal and use this kernel to sample the position buffer texture at varying offsets. For each per fragment kernel sample, we compare its depth with its depth in the position buffer to determine the amount of occlusion. The resulting occlusion factor is then used to limit the final ambient lighting component. By also including a per fragment rotation vector, we can significantly reduce the number of samples we'll need to take, as we'll soon see. As SSAO is a screen space technique, we calculate its effect on each fragment on a screen-filled 2D quad. This does mean we have no geometrical information of the scene. What we could do is render the geometrical per fragment data into screen space textures that we then later send to the SSAO shader, so we have access to the per fragment geometrical data. If you followed along with the previous chapter, you'll realize this looks quite like a deferred renderer's G-buffer setup. For that reason, SSAO is perfectly suited in combination with deferred rendering, as we already have the position and normal vectors in the G-buffer. In this chapter, we're going to implement SSAO on top of a slightly simplified version of the deferred renderer from the previous chapter. If you're not sure what deferred shading is, be sure to first read up on that, as we should have per fragment position and normal data available from the scene objects. Fragment shader of the geometry stage is fairly simple.
Alright, I guess I've got the general idea of we would go deeper later on. Ambient occlusion, PBR. We made to PBR. I don't know. I think we should do like a PBR at very beginning, and for some reason it's at the end of the book.
PBR, or more commonly known as physically based rendering, is a collection of render techniques that are more or less based on the same underlying theory that more closely matches that of the physical world. As physically based rendering aims to mimic light in a physically plausible way, it generally looks more realistic compared to our original lighting algorithms like Phong and Blend Phong. Not only does it look better, as it closely approximates actual physics, we and especially the artists can author surf materials based on physical parameters without having to resort to cheap hacks and tweaks to make the lighting look right. One of the bigger advantages of authoring materials based on physical parameters is that these materials will look correct regardless of lighting conditions, something that is not true in non-PBR pipelines. Physically based rendering is still nonetheless an approximation of reality based on the principles of physics, which is why it's not called physical shading, but physically based shading. For a PBR lighting model to be considered physically based, it has to satisfy the following three conditions. Don't worry, we'll get to them soon enough. 1. Be based on the microfacet surface model. 2. Be energy conserving. 3. Use a physically based BRDF. In the next PBR chapters, we'll be focusing on the PBR approach as originally explored by Disney and adopted for real-time display by Epic Games. Their approach, based on the metallic workflow, is decently documented, widely adopted on most popular engines, and looks visually amazing. By the end of these chapters, we'll have something that looks like this. Keep in mind, the topics in these chapters are rather advanced, so it is advised to have a good understanding of OpenGL and shader lighting. Some of the more advanced knowledge you'll need for this series are frame buffers, cube maps, gamma correction, HDR, and normal mapping. We'll also delve into some advanced mathematics, but I'll do my best to explain the concepts as clear as possible. All the PBR techniques are based on the theory of microfacets. The theory describes that any surface at a microscopic scale can be described by tiny little perfectly reflective mirrors called microfacets. Depending on the roughness of a surface, the alignment of these tiny little mirrors can differ quite a lot. The rougher a surface is, the more chaotically aligned each microfacet will be along the surface. The effect of these tiny like mirror alignments is that when specifically talking about specular lighting / reflection, the incoming light rays are more likely to scatter along completely different directions on rougher surfaces, resulting in a more widespread specular reflection. In contrast, on a smooth surface, the light rays are more likely to reflect in roughly the same direction, giving us smaller and sharper reflections. No surface is completely smooth on a microscope level, but seeing as these microfacets are small enough that we can't make a distinction between them on a per pixel basis, we statistically approximate the surface's microfacet roughness given a roughness parameter. Based on the roughness of a surface, we can calculate the ratio of microfacets roughly aligned to some vector h. This vector h is the halfway vector that sits halfway between the light L and view v vector. We've discussed the halfway vector before in the advanced lighting chapter, which is calculated as the sum of L and v divided by its length. The more the microfacets are aligned to the halfway vector, the sharper and stronger the specular reflection. Together with a roughness parameter that varies between 0 and 1, we can statistically approximate the alignment of the microfacets. We can see that higher roughness values display a much larger specular reflection shape, in contrast with the smaller and sharper specular reflection shape of smooth surfaces. Energy conservation. The microfacet approximation employs a form of energy conservation. Outgoing light energy should never exceed the incoming light energy, excluding emissive surfaces. Looking at the above image, we see the specular reflection area increase, but also its brightness decrease at increasing roughness levels. If the specular intensity were to be the same at each pixel, regardless of the size of the specular shape, the rougher surfaces would emit much more energy, violating the energy conservation principle. This is why we see specular reflections more intensely on smooth surfaces and more dimly on rough surfaces. For energy conservation to hold, we need to make a clear distinction between diffuse and specular light. The moment a light ray hits a surface, it gets split in both a refraction part and a reflection part. The reflection part is light that directly gets reflected and doesn't enter the surface. This is what we know as specular lighting. The refraction part is the remaining light that enters the surface and gets absorbed. This is what we know as diffuse lighting. There are some nuances here, as refracted light doesn't immediately get absorbed by touching the surface. From physics, we know that light can be modeled as a beam of energy that keeps moving forward until it loses all of its energy. The way a light beam loses energy is by collision. Each material consists of tiny little particles that can collide with the light ray, as illustrated in the following image. The particles absorb some, or all, of the light's energy at each collision, which is converted into heat. Generally, not all energy is absorbed, and the light will continue to scatter in a mostly random direction, at which point it collides with other particles until its energy is depleted or it leaves the surface again. Light rays re-emerging out of the surface contribute to the surface's observed diffuse color. In physically based rendering, however, we make the simplifying assumption that all refracted light gets absorbed and scattered at a very small area of impact, ignoring the effect of scattered light rays that would have exited the surface at a distance. Specific shader techniques that do take this into account are known as subsurface scattering techniques that significantly improve the visual quality on materials like skin, marble, or wax, but come at the price of performance. An additional subtlety when it comes to reflection and refraction are surfaces that are metallic. Metallic surfaces react different to light compared to non-metallic surfaces, also known as dielectrics. Metallic surfaces follow the same principles of reflection and refraction, but all refracted light gets directly absorbed without scattering. This means metallic surfaces only leave reflected or specular light. Metallic surfaces show no diffuse colors. Because of this apparent distinction between metals and dielectrics, they're both treated differently in the PBR pipeline, which we'll delve into further down the chapter. This distinction between reflected and refracted light brings us to another observation regarding energy preservation. They're mutually exclusive. Whatever light energy gets reflected will no longer be absorbed by the material itself. Thus, the energy left to enter the surface as refracted light is directly the resulting energy after we've taken reflection into account. We preserve this energy-conserving relation by first calculating the specular fraction that amounts the percentage the incoming light's energy is reflected. The fraction of refracted light is then directly calculated from the specular fraction as. This way, we know both the amount the incoming light reflects and the amount the incoming light refracts while adhering to the energy conservation principle. Given this approach, it is impossible for both the refracted/diffuse and reflected/specular contribution to exceed 1.0, thus ensuring the sum of their energy never exceed the incoming light energy, something we did not take into account in the previous lighting chapters. The reflectance equation. This brings us to something called the rendering equation 1, an elaborate equation some very smart folks out there came up with that is currently the best model we have for simulating the visuals of light. Physically based rendering strongly follows a more specialized version of the render equation known as the reflectance equation. To properly understand PBR, it's important to first build a solid understanding of the reflectance equation. The reflectance equation appears daunting at first, but as we'll dissect it, you'll see it slowly start to make sense. To understand the equation, we have to delve into a bit of radiometry. Radiometry is the measurement of electromagnetic radiation, including visible light. There are several radiometric quantities we can use to measure light over surfaces and directions, but we will only discuss a single one that's relevant to the reflectance equation, known as radiance, denoted here as L. Radiance is used to quantify the magnitude or strength of light coming from a single direction. It's a bit tricky to understand at first, as radiance is a combination of multiple physical quantities, so we'll focus on those first. Radiant flux phi is the transmitted energy of a light source measured in watts. Light is a collective sum of energy over multiple different wavelengths, each wavelength associated with a particular visible color. The emitted energy of a light source can therefore be thought of as a function of all its different wavelengths. Wavelengths between 390 nm to 700 nm nanometers are considered part of the visible light spectrum, i.e., wavelengths the human eye is able to perceive. Below you'll find an image of the different energies per wavelength of daylight. The radiant flux measures the total area of this function of different wavelengths. Directly taking this measure of wavelengths as input is slightly impractical, so we often make the simplification of representing radiant flux not as a function of varying wavelength strengths, but as a light color triplet encoded as RGB, or as we'd commonly call it, light color. This encoding does come at quite a loss of information, but this is generally negligible for visual aspects. Solid angle. The solid angle, denoted as omega, tells us the size or area of shape projected onto a unit sphere. The area of the projected shape onto this unit sphere is known as the solid angle. You can visualize the solid angle as a direction with volume. Radiance is a radiometric measure of the amount of light in an area, scaled by the incident or incoming angle theta of the light to the surface's normal as cos theta. Light is weaker the less it directly radiates onto the surface, and strongest when it is directly perpendicular to the surface. This is similar to our perception of diffuse lighting from the basic lighting chapter, as cos theta directly corresponds to the dot product between the light's direction vector and the surface normal. The radiance equation is quite useful, as it contains most physical quantities we're interested in. If we consider the solid angle omega and the area to be infinitely small, we can use radiance to measure the flux of a single ray of light hitting a single point in space. This relation allows us to calculate the radiance of a single light ray influencing a single fragment point. We effectively translate the solid angle omega into a direction vector omega and into point p. This way, we can directly use radiance in our shaders to calculate a single light ray's per fragment contribution. In fact, when it comes to radiance, we generally care about all incoming light onto point p, which is the sum of all radiance known as irradiance. With knowledge of both radiance and irradiance, we can get back to the reflectance equation. We now know that L in the render equation represents the radiance of some point p and some incoming infinitely small solid angle omega, which can be thought of as an incoming direction vector omega. Remember that cos theta scales the energy based on the light's incident angle to the surface, which we find in the reflectance equation as n omega. The reflectance equation calculates the sum of reflected radiance low p omega of point p in direction omega, which is the outgoing direction to the viewer. Or to put it differently, low measures the reflected sum of the light's irradiance onto point p as viewed from omega. The reflectance equation is based around irradiance, which is the sum of all incoming radiance we measure light of. Not just of a single incoming light direction, but of all incoming light directions within a hemisphere omega centered around point p. A hemisphere can be described as half a sphere aligned around a surface's normal n. To calculate the total of values inside an area, or in the case of hemisphere volume, we use a mathematical construct called an integral denoted in the reflectance equation as r over all incoming directions d omega within the hemisphere omega. An integral measures the area of a function, which can either be calculated analytically or numerically. As there is no analytical solution to both the render and reflectance equation, we'll want to numerically solve the integral discretely. This translates to taking the result of small discrete steps of the reflectance equation over the hemisphere omega and averaging their results over the step size. This is known as the Riemann sum that we can roughly visualize in code as follows. By scaling the steps by dw, the sum will equal the total area or volume of the integral function. The dw to scale each discrete step can be thought of as d omega in the reflectance equation. Mathematically, d omega is the continuous symbol over which we calculate the integral, and while it does not directly relate to dw in code, as this is a discrete step of the Riemann sum, it helps to think of it this way. Keep in mind that taking discrete steps will always give us an approximation of the total area of the function. A careful reader will notice we can increase the accuracy of the Riemann sum by increasing the number of steps. The reflectance equation sums up the radiance of all incoming light directions omega over the hemisphere omega scaled by fr that hit point p and returns the sum of reflected light low in the viewer's direction. The incoming radiance can come from light sources, as we're familiar with, or from an environment map measuring the radiance of every incoming direction, as we'll discuss in the following chapters. Now the only unknown left is the fr symbol, known as the BRDF, or bidirectional reflective distribution function, that scales or weighs the incoming radiance based on the surface's material properties. The BRDF, or bidirectional reflective distribution function, is a function that takes as input the incoming light direction omega, the outgoing view direction omega O, the surface normal n, and a surface parameter that represents the microsurface's roughness. The BRDF approximates how much each individual light ray omega contributes to the final reflected light of an opaque surface, given its material properties. For instance, if the surface has a perfectly smooth surface like a mirror, the BRDF function would return 0.0 for all incoming light rays omega, except the one ray that has the same reflected angle as the outgoing ray omega, at which the function returns 1.0. A BRDF approximates the material's reflective and refractive properties based on the previously discussed microfacet theory. For a BRDF to be physically plausible, it has to respect the law of energy conservation, i.e., the sum of reflected light should never exceed the amount of incoming light. Technically, Linfong is considered a BRDF taking the same omega and omega as inputs. However, Linfong is not considered physically based as it doesn't adhere to the energy conservation principle. There are several physically based BRDF out there to approximate the surface's reaction to light. However, almost all real-time PBR render pipelines use a BRDF known as the Cook-Torrance BRDF. The Cook-Torrance BRDF contain both a diffuse and specular part. Where KD is the earlier mentioned ratio of incoming light energy that gets refracted, with Ks being the ratio that gets reflected. The left side of the BRDF states the diffuse part of the equation denoted here as F Lambert. This is known as Lambertian diffuse, similar to what we used for diffuse shading, which is a constant factor denoted as.
Oh, this is what just happened? Normal distribution function, geometry function. What is this?
The Fresnel equation, pronounced as Fresnel, describes the ratio of light that gets reflected over the light that gets refracted, which varies over the angle we're looking at a surface. The moment light hits a surface, based on the surface to view angle, the Fresnel equation tells us the percentage of light that gets reflected. From this ratio of reflection and the energy conservation principle, we can directly obtain the refracted portion of light. The ambient occlusion, or AO map, specifies an extra shadowing factor of the surface and potentially surrounding geometry. If we have a brick surface, for instance, the albedo texture should have no shadowing information inside the brick's crevices. The AO map, however, does specify these darkened edges, as it's more difficult for light to escape. Taking ambient occlusion in account at the end of the lighting stage can significantly boost the visual quality of your scene. The ambient occlusion map of a mesh/surface is either manually generated or pre-calculated in 3D modeling programs. Artists set and tweak these physically based input values on a per pixel basis and can base their texture values on the physical surface properties of real-world materials. This is one of the biggest advantages of PBR render pipeline, as these physical properties of surface remain the same regardless of environment or lighting setup, making life easier for artists to get physically plausible results. Surfaces authored in a PBR pipeline can easily be shared among different PBR render engines, will look correct regardless of the environment they're in, and as a result, look much more natural. In the previous chapter, we laid the foundation for getting a realistic physically based renderer off the ground. In this chapter, we'll focus on translating the previously discussed theory into an actual renderer that uses direct or analytic light sources. Think of point lights, directional lights, and slash or spotlights.
This should be in the beginning of the book. Why it's at the end of the book? It's like, who cares about obsolete rendering techniques? It's like I'm tired implementing it. I would probably need to implement it, but yeah, anyways. So this is all PBR rendering, and it's I mean, it's just a bunch of formulas, but there is algorithm. You just copy paste it and it just works, right? I mean, you need to have some understanding on it, but I guess on high level I do understand, so who cares? What is this? IBL.
In the previous chapter, we've set up PBR in combination with image-based lighting by pre-computing an irradiance map as the lighting's indirect diffuse portion.
Image-based lighting.
In this chapter, we'll focus on the specular part of the reflectance equation.
Image-based lighting. So essentially I need to figure out how to set this way of rendering. It's like I have a renderer, but it's not PBR renderer. Oh, why it's gray? I need to comment out stuff. Right, so I need to make the PBR renderer. Anyways, let's finish the book, and I think I probably will start a completely new repository. Look at this, how pretty all this stuff. debugging. Who cares about debugging? We know how to debug stuff. I mean, we do not know how to debug stuff, but we kind of built some sort of intuition going through all these tutorials. So I think the book is done. It's like and PBR should be at very beginning. Should start from PBR. Text rendering, blah blah blah. Let's go to the lighting, model loading, advanced lighting, PBR in practice, and making the game, render text, audio, power ups, post processing, particles, collisions. Yeah, I think we're done with the game. Not the game, with the book. I think I will create new project and would try to implement PBR rendering with what is it? Deferred rendering. It's like we have models and load models as a PBR models. We would need to, yeah, anyways. So I think we need to have a new, at least I've got the ideas how like shaders working, how to set up shaders and set up other things. Formulas we can just get from the book or maybe from examples. Yep. So they have some 2D game, particles effects. So this is a 2D game. Did they make only 2D game? Did they have any 3D games? Breakout. Oh, it's only 2D game. Hey. Okay, I think it's only 8 p.m. but I'm so tired. I woke up at 12 and I'm so tired. Also, my son got sick and I feel like he's infecting me. It's like then I start streaming, I was coughing and it's like it was hard, have a hard time to talk. Right now I feel kind of better, but I feel really really tired. So I think it's okay if I'll not to push. I don't think I should ever push myself. So like if I feel tired, I just need to rest, and you know, even if I die tomorrow, I would not know I die. So like I'm just pretending I'm going to live forever, because who knows, maybe I will live forever. So like if I'm tired, why to feel miserable? Let's take a rest and enjoy the life, right? Okay, thank you for watching and see you next time. Bye.